So we will start from where we left off in the last class. In the last class, we were looking at the different types of test cases that the verification engineer is required to write for testing a circuit. So we said that among the scenarios that are to be covered, we can break down that scenarios into 6 different categories, and those categories were as follows. The first category of tests are uh, for checking whether the design is able to function properly when some invalid inputs are specified. Now, in reality, invalid inputs can always come, and we want to make sure that the design works in a consistent way when invalid inputs come. The second category of tests was that if we start from an invalid state, whether the design is able to recover from that and enter a valid state. The third category is the set of scenarios in which the design moves from a valid state to an invalid state uh, even when a valid input has been given. So these are the set of scenarios which represent bugs, right? And then the most standard scenarios are the next one, where you can go from any valid state to any other valid state on a valid input. And then finally, the categories 5 and 6 are for power on. So when we switch on the power of the design, at that time typically the system is in some arbitrary state, and we want to make sure whether it eventually reaches a valid initial state. And the last category is that whether it fails to do so. Now, this represents all the possible scenarios that are possible, right? And the engineer who writes the verification plan must write tests targeting each of these categories. Right? Some of these categories might be empty also, because there may not be a bug. So you may not find any case in one of those scenarios, but still we have to write tests to see if those scenarios can be covered or not, right? So let us take an example of a disk controller to demonstrate the notion of developing these kinds of tests. So as you might be aware that a disk is typically partitioned into concentric circular strips, which are called tracks, and each track is partitioned into blocks which are called sectors. So our disk controller has 6 types of registers, namely that there is a command register which contains the command that is being performed on the disk, in the sense that whether it's a read or a write or whatever. Track represents the track number on which the read, write, etc. is taking place. Sector is the sector number at which that is taking place. Data out is the data to be written into the disk, and data in is the data read from the disk. Okay. And status shows the state of the disk and the status of the operation. We will see that status has several flags and they have their own meanings. It is there in the next slide. The commands are of the following types. Restore is one of the commands which determines the head position when the disk drive is first turned on. Now, when the disk drive is first powered on, the head position is at some point. It may not be at one end of the thing, but maybe at any intermediate point. So when you drive the restore command, at that time it is going to determine the head position and return that. Then we have a seek, then step in, step out, read, write, read sector, write sector, read address, read track, write track, etc. Okay. So these are the different commands that are supported by the disk controller. So let us look at the structure of this. So this is the interface. Okay. There are the signals like read, read, write, okay, then data request, address lines, and the data lines, etc. And these are the registers which we just now described, and there is a status register which has these 8 flags indicating different kinds of things like lost data, or whether the motor is on. If the record is not found, then this flag is going to be set high, and things like that. Now let us take some examples of of those 6 categories of tests, right. So, let us look at the first category. This category represents those tests where we want to drive the design from one state to another on an invalid input and see how it reacts to that. So, for example, that you could test the controller by providing an address which is in a forbidden range. Typically, most of the devices that are used are the I/O is address mapped, in the sense that if the address is within certain range, then the device knows that this is the address for my range of things. If it is outside that range, then it assumes that it is for some other device, right. So, if we have that kind of memory mapped I/O, then what you can do is you can drive addresses in a forbidden range to see how the disk controller reacts to that. Then set the controller in an illegal state. This is the second category, such as you give an illegal opcode in the command register, which is not an opcode corresponding to the set of commands that we saw in the previous slides. And you could put out of range data in the track and sector registers, put some value of the track register, and there is no track of that number, let us say, right. So, that's putting out of range data in the track. Similarly, you can do out of range data in the sector register and see whether the controller detects the problem and recovers from it. Then suppose we want to try to drive it into invalid states, which is the third category. So, given the head position, we are trying to figure out, are there track values that would produce a wrong value from signal direction. The direction is the direction in which the head moves, okay. And have you heard of the elevator algorithm, which is typically used by the disk controllers? No, what it does is, in an elevator, as the disk requests come, access request for the disk comes. So, have you seen how the elevator works? Suppose you have an elevator and you want to go up, right. Now, if the lift is coming down, then it will continue to go down as long as there are requests in the down direction, and when it has completed all requests in the down direction, then it is going to reverse the direction to up and then again start moving up, right. So, there are cases where you want to go up and you will see the lift just passing right in front of you and it is going down, but it does not stop for you. That is because of that algorithm, right. So, similarly, disk controllers also maintain that direction, and it is the same algorithm that is followed in terms of the movement of the head across the tracks. So, what we are trying to see here is, given the head position, are there track values that would produce a wrong value from signal direction, right. So, that is kind of trying to test whether there is a bug in those behaviors. And then we try to, let us look at the fourth category, where we try to establish that it reaches only valid states from a valid state. So, for example, for given values in the track and sector registers, are the outputs from the step and direction correct, right. Now, see, there is a very thin margin between the category 3 and category 4, right. Here we are trying to look for bugs, here we are trying to look for the coverage of all different kinds of scenarios, right. Now, typically this, when we look for bug, we look at the corner case scenarios and things like that, and this is generic, to see that the normal functioning is correct. But it is very thin, I mean the line between the two. So, you can actually think that they are actually the same category, and if you find a bug, then it goes into the first one, and if you do not find the bug, then it goes into the second one. Then look at the power up scenarios. So, for example, we can try to see what are the values of the registers when the controller is first powered on. Are these values correct or expected? So, we make sure that whether the disk controller initializes all the registers with some valid value at power on, or immediately after power on, do registers track and sector, the track and sector registers, do they contain the correct track and sector number of the head position if the restore command is executed? I mean, the restore command is supposed to do that. When you execute the restore command, it should be the case that the track and sector values capture the correct position of the head, right. So, you test that whether that is indeed happening or not. Then again, now in order to test this one during simulation, what do you need to do? You need to remember where the track and sectors were in the previous simulation, then bring it to power down and then power it up once again and see whether it can read that same value or not. Now, under what conditions will the controller enter an illegal state on power on? This is the type of scenarios that we try to see in the last case, right. So, this is just to give you an overview of the ideas that verification engineers use to build the test plan. This is done completely manually, and for each category tests are built, right, and documented before they are actually the test benches are written. So, this test plan document is an English language document which contains the set of tests that are to be run. Right. And we saw in the last class that if you cover all of these categories adequately, then we showed that it essentially is covering the whole set of possible scenarios. Now, what we have talked about so far is called directed test generation, because you identify each of the different categories of tests, you identify the individual tests, and then for each of those individual tests you write a test bench, right. For a large design, there are going to be thousands of such test cases, and the verification engineer or the verification team will systematically write down each of these test benches and run each of those test benches on the design, right. This is the directed test approach. Now, with the increasing complexity of the designs, this is becoming very infeasible. So, people are trying to move into randomized test benches, and that is what is the current popular trend. What is a randomized test bench? That instead of writing directed tests for each of these scenarios, we have a randomizer with just spins of tests, right. Now, if you just randomly drive different tests, then you will get a lot of coverage very quickly, because it is going to, that time that you spend in writing down those test benches is not there, the time that you spend in planning this test plan is not there, right. But there are two very important issues. One is that your random test bench must depict a valid environment behavior, right. Otherwise, there will be lot of tests which corresponds to invalid environment behavior, and while that is also one category of test that we want to run, we do not have that as a very high priority item. It is more important to make sure that the design works correctly in the intended environment. So, the intended environment has to be modeled by the random test bench. Now, that is not easy if you are doing it randomly, right. There are specific constraints on the behavior of the environment of the design. Like for example, if you have a design, some peripheral which is sitting on a system bus, right, and it is communicating with the other devices through that bus protocol, then the interface of this device has to be compliant with that protocol, right. You cannot just start communicating with the other devices following your own protocol, right. So, that means that when I want to test this device, then the test bench has to be compliant with that protocol, because if the environment starts behaving, starts violating the protocol, then you cannot really design a device which is still going to communicate correctly, right. It may detect that anomaly and may go to some reset state or whatever, but it is not going to be able to function correctly, right. So, to test the functionality of the design that you want to test, you will have to model that environment also in the random. This is one important requirement. The second important requirement is that how do we know that what fraction of those behaviors have been covered? We noted down all those 6 categories, and within all those 6 categories, typically a verification engineer is going to write down those English language test scenarios, right. Now, when you write one randomized test bench, how do you figure out that which of those tests have actually been covered? So, we need to have coverage monitors. We have to have monitors which is going to track that which of those scenarios have been covered, which scenarios are yet to be covered, alright. Typically, a randomized test bench is not going to go into low probable scenarios very quickly, because the randomizer follows certain probability distribution, and if you have a very unlikely scenario, okay, then it is going to be the randomizer will not be able to reach that very quickly. For example, suppose I say that in a system there are 5 devices which access some common resource, right. Now, let us say that the probability that one of those devices is making a request at a given point of time is 10%. So, that is not a very low probability. Once in every 10 cycles it may be making a request. Now, suppose we want to figure out what is the probability that all 5 of them are requesting at the same time. They all raise their requests at the same time. So, this is going to be 0.1 into 0.1 into 0.1 into 0.1 into 0.1. So, that is 0.000. So, the probability of that is much lesser. Now, there may be something that you do when all 5 devices are requesting together, right. So, a random test generator may not throw up that scenario very easily because of the low probability of that. So, the third important point is that there are times when we will have to bias the random test generator, so that it is able to go into those corner case scenarios which we want to test. Right. So, typically today this is handled by writing a random test bench, monitoring whatever coverage it does within some reasonable amount of time, and then covering the remaining corner case scenarios through directed tests, alright. And there are new technologies which are coming up, where that last portion of writing the directed tests is avoided by cleverly biasing the random generator, so that the randomizer itself drives the simulation into those scenarios. So, let us look at some of the stuff that is supported today. So, this is a typical system Verilog test bench with which uses pseudo random test generation. So, this is just a toy example. So, suppose we have defined a bus which is a 16-bit bus called ADDR. So, that is the address bus, let us say. So, in system Verilog you can define a class like this, okay, which represents this data, right. And then here we are defining B1 to be a bus of this type, right. So, equal to new means this is the constructor, right. So, now B1 is a bus, right. Now, we are going into the actual test bench. Now, we shall see the structure later on. You see, the whole of the test bench comes in the initial block, right. The whole of the test bench comes in the initial block, where you just call a set of tasks. We will go into this test bench design through some demonstrations later on in the coming weeks, when I will show you exactly how a complete test bench how it looks like. Now, what this statement here is doing is that it is calling a randomize function. So, it is saying that randomize B1, okay. Now, that means that the data that is available here, the variable that is available in V1, namely this ADDR, is going to get a random value, right? But there is a constraint. So you can specify a constraint saying that randomize this thing with ADDR less than equal to 128, which means that it's going to pick up some random value which satisfies this constraint. And you can give more complicated constraints also, like B1 dot randomize with ADDR greater than 128 and ADDR less than equal to 1024. If you have more than one data items here, your constraints can involve more than one data item also. So you can say that this plus this is greater than that plus that, right? You can do that. So it employs a full constraint solver inside to generate the random values corresponding to that. Okay. So that's roughly the way in which you can, inside your test bench you can randomize the values of different variables. Right? Now, for a complete test bench, as I said, that you need to develop a valid model of the environment. So suppose this is our design under test. Okay. And now in order to test that, what we need to do is to develop the models for the other components in the system. So what we are trying to test is some master device here maybe, right, or some slave device here. So in order to model this, we will model other master devices, we will model the clock generator, we will model the memory, and maybe even a processor, okay, which consists of the other components in your full chip, right. Now how do you model this? So there are the system Verilog test bench language has very rich features for doing this modeling, right. It's almost C like, it's very rich. You can have multiple processes, you can fork, you can join, then you can have semaphores for communications between those, synchronizing between them, right. We are going to have one special lecture on system Verilog test benches later on. So by that you can model all of these quite easily. And then there is the test generation engine, which is going to use these models and those randomized commands which are embedded inside these to run the simulation and generate different tests. And then we have coverage definitions, which we will see in the next thing, where you can monitor how much is being covered. Okay. And the third thing is assertions, which we are going to look at in the next lecture. A typical layered random test architecture is going to look like this, where you will have the design under test, and then the whole test bench is organized into different layers. I will give you some examples of what these do. So the lowest layer, the driver layer, is the one which is actually driving the signals into the DUT. Now see, all this is software, right. This is all driven by the simulator. So the lowest layer is the actual protocol that you are doing, right. So for every basic transactions, you will write a set of statements in the driver layer to drive that. So for example, getting access to the bus, that means you send a request to the arbiter, wait for the arbiter to provide the grant. So that's getting access to the bus. Then you want to start driving a read transaction, for example. So you float the address in the address bus, then wait for the slave device to respond by putting the data, right. Then you latch the data. If that slave device is not ready, then you will have to wait until it becomes ready. So all this is done at this layer. The next layer is the one which executes transactions. So this is the one which is, for example, if you have a burst read transaction, that means that it's going to do this for several cycles. So the controller which actually, at the lower layer, it is the actual interaction that is taking place. The next higher layer, I am driving all the steps of the burst read transaction. Right. When you go one layer higher up, then it creates random transactions. It decides that is the next transaction going to be a read or a write or a burst read or a burst write. Okay. So, that sequence of transactions is decided by the next higher layer. Right. Now, see, each of these layers, they are communicating with the lower layers. So, when we create random transaction sequences, so read followed by write followed by a burst read followed by 2 writes, right. So, when we create this sequence, this layer is just going to tell the lower layer that now you drive a read. Right. When the lower layer completes a read and says that I am done, then you say I now you drive a burst write. Right. So, this is what is happening, and they communicate with certain primitives called channels. Right. Now, you remember the network stack, the layers in a network stack. You have the data link layer, the physical layer, then the data link layer, right, then the transport layers, right. So, those are, this is very similar to that. So, there also you see we want to shield the upper layers from the intricacies of the lower layers. That is why we do this layering. Right. We will, when we go into the demonstration, we will see an example of a layered random test bench, where all these things will be there. Then you have these tests which creates the interesting conditions, right. So, these are the high level scenarios that you want to create. So, you can model them there, and then the whole stack automatically drives it down below with the appropriate randomization of the data and control. Then we have the monitors which observe the data from the design under test. There is the checker which identifies whether what transaction was performed, because we need to correlate that what transaction you wanted to execute is actually the transaction that has happened here, right. And then we check correctness, we check whether this and this are correct, that is that what I expected out of this here is what I got out of this. Now, self checking is a very important thing if you want to have a random test generator, because you see in a random testing you do not know what test is going to be driven. So, how do you know what is the golden output, right. So, there has to be a mechanism from the test bench layer to produce the golden output, and then you match that with the simulation output, right. So, typically you would use a model of the design under test here as well, by virtue of which the transactor layer will generate the correct or expected output, and you use the actual duty to simulate and find out the simulation output, and then compare the two, right. This happens automatically all the time. And then we have the assertions which we will discuss shortly. Now, this picture shows that what is the gain in productivity by this new approach. So, in the previous traditional approach, which is shown by this red colored line, you start developing the test plan. That's what is happening here. The test plan is developed here, and then you start coding the directed test benches for each of those tests, right. As you start coding them, you see the coverage grows, the number of test cases grows, because you write one directed test bench. So, when you simulate that, your coverage grows a little. Write the next directed test, it grows a little more. Write the next directed test, you have covered a little more. Okay. Now, see, there is a manual effort here. You have to write each of those test benches and then drive it. So, this only moves in a certain slope, and the slope is determined by the number of people who are working in the verification, right. If you have more number of people, this is going to go more steeply. Now, in the new approach, which is becoming predominantly the more popular approach, we take a lot of time in building those models. So, you see there is a significant amount of time spent here where there is no growth of coverage, right. Why? Because that is when we are writing all those models. we are developing the self-checking random environment, and then once that is done, then there is no manual involvement anymore. You just run your random test bench, it starts covering all those test cases, and you just monitor the coverage. So you see there is a very steep rise in the coverage immediately when this is done, right, and then it keeps on growing at a very fast rate until again that also reaches a saturation. Now when does it reach a saturation? When your random cases has covered all the common scenarios, and the only scenarios that are left are the corner case ones which are difficult to reach by randomization, right. That is when this is going to get tapered off, right. But typically you are reaching a very high level of coverage much faster than the directed approach. So this is the productivity gain. So you are reaching here much faster than you would have reached otherwise, right. And remember that this verification is going to eat up 70% of your design cycle time. So this productivity gain is a very significant amount, because it is, you know, if you are able to reduce 30% also, so it's 30% of the 70% of the time. So that's pretty good, right. So this is the motivation for this. Now let us quickly go through the ways that we estimate coverage. So there are broadly three types of coverage metrics that are used. One is called code coverage, which checks how thoroughly the code of the design is exercised. For example, if you take a FIFO, a queue, you want to check the percentage of the RTL code of the FIFO which is simulated by a simulation suite, right. So that is what we mean by code coverage, right. Then we look at parameter coverage. Parameter coverage checks the extent that dimensions and parameters in the functional units are stressed. So for example, we want to check the range of depth that a FIFO encounters during simulation. Now you see, in a FIFO I might be writing 2 items, reading of 1 item, writing 3 items, reading of 2 items. If we do it like that, then the number of items in the FIFO at a given point of time is going to be very less, right. Now you might want to make sure that you are covering all cases up to the point when the FIFO is either full or almost full, right. So that's the range of depth that we are talking about here. And also you know, the FIFO may be parameterized. So you may try to see whether a FIFO of capacity 2 is working correctly, whether a FIFO of capacity 1024 is working correctly, and so on, right. So that's another aspect. Typically parameter coverage also looks at, you know, different kinds of you know, if you can work with variable bus widths, right. So you want to make sure that for what kinds of widths you are able to verify that. Functional coverage accounts for the amount of operational features of functions in a design that are exercised. So for example, we want to see that whether we checked all the operations like push and pop for the FIFO, and all the conditions like full and empty, that whether the queue is full or whether the queue is empty, and whether we checked all those cases. So this last part is typically manually enumerated, and then you write coverage monitors to track the coverage of each of those items, right. We will see how we do that. So let us start from one side of the story where we look at statement coverage. So here we collect statistics about statements that are executed. So now suppose in one simulation we find that A is greater than X and X is equal to Y. Then which lines of code are going to be covered? So these ones, because this is always going to be covered. These two lines are always going to be covered in every clock cycle. Then I check if A is greater than X. If it is true, then these two lines are covered, and then this is not covered because we don't go to the else, and then again this is covered because X is equal to Y, and this is not covered, right. So this is the code coverage corresponding to the scenario where A is greater than X and x is equal to y. Now, we could track the changes in each of these lines of code, or whether each line is covered or not, but a better option is to do what is called block coverage. So, see, we observe that if this statement is executed, then this is also going to be executed, right. So, they are in the same block. You cannot execute one of them without executing the other, right. So, we club those blocks together. So, this is one block, this is one block, this is one block, this is one block, and this is one block, and then you monitor the coverage of the blocks. So, from the block coverage you can also get the statement coverage, okay. And it makes sense to do this because you will have to write fewer points of monitoring. So, to check whether this is covered, we need to put some monitor here to make sure that it has entered here, right. So, for example, if you want to do the monitoring using some print or display messages, you will have to put a display here, a display here, a display here, and so on, right. The other thing that people like to look at is path coverage. Now, path coverage is different from statement coverage or block coverage, in the sense that there we want to look at every possible path in the control flow graph of the code. So, this is the control flow graph. So, we have a branching at a greater than x, and you could take this branch or this branch, right, and then again we have a branch for x equal to y, and you can take this or this. So, how many possible paths are there? There are 4 possible paths, right, from beginning to end. One is the one which is shown here. Then you could have another which goes like this, but then takes this one. So, this is another. Then you can have this one, and you can have this one followed by this one. Okay. So, 4 different paths. So, if we take if we simulate only this path, then we have 25% path coverage, right. If you take this path and this outer path, then you have 100% code coverage, but only 50% path coverage. Is that clear? What I am saying is that if you cover this path also, then you have 100% code coverage, because you have covered all the statements, 100% rather block or statement coverage, but not 100% path coverage, because the remaining 2 paths were not covered. Now, the limitation of this approach is that the number of paths grows exponentially with the number of conditional statements. So, if you have k such branches, then you could have 2 to the power of k paths, right, and that is a phenomenal number. So, typically we are not able to do that coverage. By the way, if you do 100% path coverage, does it mean that you have exhaustively tested everything? No, because still there is the data, right. The data can take different values, and there are very interesting corner case scenarios which depend on the data, like overflows and things like that. So, we have to be careful that even if we have 100% path coverage, it is not 100% functional coverage. Now, expression coverage means that we have these expressions, and we want to see whether we have covered all possible ways in the expression becomes true, right. So, for example, if I take x1 x2 plus x3 x4, this evaluates to 1 in many different ways, right. So, it evaluates to 1 when x1 x2 is 1, it also evaluates to 1 when x3 x4 is 1, right. But x1 x2 can be 1 in only one way, that is both x1 and x2 are 1. So, there are no choices there. x3 x4 also can be 1 in only one way, right. So, essentially to cover this expression, we need to look at only 2 types of cases. When both of them, when this is 1, this is something else, 0 or 1, I do not care, and when this is 1 and this one is something 0 or 1, I do not care, right. So, if we cover these 2 cases, then we have covered all cases for this expression, right. So, to do expression coverage, we use what is called a minimum input table. A minimum input table is a list of minimum input determining an expression, right. So, a minimum input determining an expression is the fewest number of input variables that must be assigned in order for the expression to have a Boolean value. So, let us look at x1 and x2. Function is f equal to x1 and x2. Now, you see, if you make x1 0, then the rest is do not care, the function value immediately becomes 0, right. So, this is one minimum input determining case. Similarly, if you set x2 to 0, it is determined. And the third case is that if you want this to be 1, then both of them has to be 1. So, the minimum number of inputs that we need to determine in order to make this 1 is 2, right. This is another function which is f gets the value of x1 if y is true, otherwise it gets the value of x2. So, if the value of y is 1, right, then the function value depends only on x1, right. So, you have 1 here, 1 here, 0 here, 0 here. If the value of y is 1 for these two cases, the value of x2 does not matter at all, right. Similarly, when the value of y is 0, then f is getting the value of x2, so the value of x1 is not care, right. So, why do we create this minimum input table? We will monitor during simulation which of these cases have appeared, and we will put a tick that yes, this case has been covered, this case has been covered, right. And then we will monitor what is the percentage of coverage. So, for complex expressions, we cannot continue to do this because it is going to grow like the truth table, right. So, we decompose it into layers. So, if we have this as an expression, then we can break it down into two components. So, this is f1 and this is f2, right. So, f1 is x greater than y, f2 is a and b, and f is f1 or f2, right. Now, when we talk about the coverage of f, we will see how many times f1 has become true, how many times f2 has become true, right. We are not going to look inside the expressions of f1 and f2 to determine what are the coverage of its components, right. That is what we mean by decomposing it into layers, right. Now, let us take this example. Suppose we have this expression, and suppose simulation covers these two cases, that is XYAB is 3411, and in another simulation we have covered XYAB is 2510, and we want to figure out how much of expression coverage have we got. So, now let us see that in what is the value of f1 in each of these. What is the value of f1? f1 is x greater than y, right. So, is it true here? No. So, here f1 is 0. What about this? Here also f1 is 0, right. Now, so in both of these cases f1 is 0, right. What about f2? f2 is a and b. So, this case is 1, for this case it is 0, right. So, now let us look at the minimum input table of f. Right. In the minimum input table of f is OR, right. So, to make f 0, both f1 f2 has to be 0, and to make f1 we can make f1 as 1, then the other one does not matter, or f2 as 1, in which case the other one does not matter, right. Now, in our case f1 is only 0 in both of these cases, right, and f2 is 1 in one case and 0 in another case, right. So which of these entries have we covered? Have we covered this one 0 0 0? Yes, because in the second one both of them are 0. Have we covered this one where f1 is 1? No, there is no case where f1 is 1. Have we covered this one? Yes. So out of the 3 we have covered 2. So we get a coverage of 2/3, right. So 2/3 is 66.67%. Right. Similarly, let us look at the coverage of f1. What is the coverage of f1? f1 is 0 in both of these cases, so only this one has been covered, right. This one has not been covered, so we get a 50% coverage. Then look at the coverage of f2. f2 is 1 here and 0 here, right. So have we covered this case, the last one? We have. So this is this one, A and B both 1, so this is covered. Have we covered this one? Yes, because in this case 1 0, right. So we have covered this one. Have we covered the top one? No, because in none of these cases is A 0. So we get 66.67% coverage of f2, right. Now see, this is just breaking down the coverage analysis into different levels of granularity. I could have taken this single expression and developed a minimum input table for the whole expression and then analyze its coverage, but that would have been computationally difficult because the number of rows in that table can grow exponentially with the number of input or number of variables in the function, right. So we adopt this kind of approach. Then we look at state coverage. Now state coverage calculates the fractions of states visited during simulation. So you look at the different, you extract the state machine from the RTL code, and then during simulation you track which of these states are covered, right. So initially you are here, then you see that you are visiting S2, then you see you are going back to S1, then S2, then S1, then S2, then S1, and then you finally say that S3 and S4 were not covered. Now that means that S4 cannot actually be covered because it is unreachable from S1, but then S3 can be covered because we did not drive the correct simulation, maybe we missed out simulation cases, which is why S3 was not covered. So you may not always get 100% state coverage because 100% of the state space may not be reachable, right. So there is always, you have to figure out that what percentage is reachable, and then based on that you decide whether you need to run more simulation to improve state coverage or not. There are various other variants of the state based coverage metrics, like you can track the number of transitions of the state machine that are covered during simulation. You can look at sequences. Now sequences are typically user defined state sequences. You want to make sure that these sequences have been covered, right. We will see later on that in assertions you can specify sequences to monitor sequences. And then another popular metric is toggle coverage, right. How many nets, how many nodes, how many variables, ports, etc. were toggled. Right. Now to check all this coverage, we need to do what is typically called an instrumentation of the RTL code. We need to plug in appropriate things within the RTL code so that these coverages can be monitored, right. So for example, this is an instrumented PLI. PLI is this programming language interface. So what we are doing here is that, see, it is the same code that we saw previously, except that we have inserted these calls. What does this call do? when we call C1, it gets the simulation time using some get time function, right, from the simulator, and then it increases the frequency of the number of calls to C1 at that time. Right. So it says that so this is a array which is monitoring the number of calls to C1 at each time t. Right. So in fact, in the same time t, this may be covered many a number of times. You realize that that can happen, right? Because this triggers something, then that triggers something, and again this is simulated in the same simulation time, right? So similarly, you can have C2, C3, etc., and you can also have PLI for computing expression coverage sitting inside that. So for example, we had y equal to b and a here. You might be interested in finding out how many times was b1, how many times was a1, right? And based on that, you compute the expression coverage of that. Now, typically, what happens is that most of the simulators that are there commercially available today, they support what are called callbacks. And these callbacks are part of the standards of system Verilog, right? So there are certain callbacks. What are these callbacks? These callbacks are specific points in the simulation where you can add a callback. What happens is when the simulator reaches that point of the simulation, it is going to call your function, right? And you can put whatever you want in that function. So you can put some coverage analysis code there, you can do anything of your choice in those functions, right? And these callbacks are very useful things for interacting with the simulator to collect different kinds of statistics and work on that. Okay. We are going to look at one simple example for functional coverage analysis, and we are going to close this chapter with that. So suppose we have two processors, processor A and processor B, which are communicating through a system bus, and they have their own individual caches. Right? So cache of processor A and cache of processor B. Right? Now, this table shows an example of the kind of functional coverage tests that you typically want to develop. Right? Now remember that this functional coverage, because it talks about the functionality coverage, so it has a manual component in it, and that manual component is in understanding that what kinds of scenarios we need to cover, right, and then defining that that these are the things that we have to do, and that is then translated into coverage monitors and feed it into the test architecture, right. So as of now, just let's see that let us look at this example, that we have the following sequence. So this is a sequence, remember, it is not just one test and it is not independent, 4 independent tests, it is one test after the other. So suppose we first do the following thing, processor A reads D. Now D is some data item, right, and at that time the position of the cache was cache A was empty, cache B was empty. The action is that it will read from main memory and mark that cache to be exclusive, that data to be exclusive in that cache. So now after this is done, D is going to be in cache A and it will be marked exclusive in the sense that it is not there in B. Next thing is processor B reads D, and at that time D is already in A. So what is the action that the controller should do is that it should copy D to cache B, because it is available in cache A. So it is going to copy D from cache A to cache B and make both copies shared. So now it is there, because we make it shared because we want to have cache coherence, right. See, we marked it exclusive if if processor A wanted to work on D at this point of time, it will not have to update cache B because it is exclusive data. But now it has become shared. If one changes it, it has to reflect on the other cache also, right. Now processor A writes D. Now it is shared, remember. So invalidate all copies of D, update cache A and mark it modified, right. So what happens is that at the result of this, cache A contains D, which is indicated as modified. Why do we indicate it as modified? Because we have to write it back. Right? We have read it from the memory and modified it in the cache. So it has become dirty. We have to write it back. And what does cache B show? It has no D. Now look at processor B reads D. What happens? We deposit D of cache A to memory, right. We write back D from cache A to memory, copy D to cache B and then mark them shared. Right. Now this is because the policy says that when the other processor is trying to read D, at that time we must first do a write back and then make it shared and then make it accessible to processor B. So this is to give you an example of the types of functionalities that the verification engineer wants to cover. Now you have to make sure that each of these cases are actually covered in simulation, and we need to plug in coverage monitors for each of these cases, right. When we study assertions, we will also study how we can write coverage monitors for these kinds of tests, right. So functional coverage, one of the good ways of monitoring functional coverage is by writing coverage monitors using assertions, right. We are going to see that in the next lecture. So that brings us to the end of